the cloud. Hello, I am Justin. I will be the one who teaches you math. The class is polynomials. The TA is Luke Robitaille. Some of you might have heard of him before. All right, great. That's who we are. Let's do polynomials now. These are examples of polynomials that we went over before everything fell apart. So 5 is an example of a polynomial, just any constant function. Looks like this. All right, x plus 5 is also a polynomial, right? Any linear equations are polynomials, and I'm hoping that you've all seen these before, maybe in solving systems of equations. So we have also these things like quadratics, all right? And they look something like this, maybe. Yeah. All right, any quadratics work. All right, can anybody think of any other like more general examples of polynomials? And if I ask questions and you guys want to respond, feel free to respond to me also. Are there any other types of polynomials that maybe we could think of? All right, I see cubic. Cubics, let me use a different color. Looks something like that. All right, maybe you could also click that. And in general, so what does a cubic look like actually? Like say something like x cubed plus 2x squared plus x plus 9. This is the cubic. You can see that there's a 3 right here. And hopefully you all are beginning to pick up on the general structure. These coefficients in front of these terms, we don't really care about too much, but these exponent terms are really what makes the polynomial. So we can write it in a general form. All right, we can start with the coefficients. All the way down to the linear term and then the constant term. Now, you'll notice that there are some very important exponents that I'm missing. All right, I have 0 through n right here. You can think of this as an x to the 0th and this as an x to the 1. But what am I missing? What exponents of x am I missing? Wait for a couple more people to answer. Everything in between, that's an interesting one. Yeah, so I don't, that's important too. I can't have like an x to the 1.5. Right, we can't really represent this as a polynomial because this isn't a simple product of x terms. All right, another thing. Yeah, we have to have integer exponents, but there's another entire class that I'm missing. All right, and that class is negatives. I can't, if I just like added like 1 over x and 1 over x squared and so on, this is not a polynomial. And the reason for that is mainly convention and also because it makes a lot of operations nice. A lot of operations nicer. Whoops. So this is going to be the only form of a polynomial that we look at. However, I'm missing an entire like dimension of polynomials. Does anybody have any idea what I'm thinking about? What do I mean dimension? I mean just like another like category, basically. I see absolute value. That's close, but it's actually not a polynomial. I'm seeing a lot of people say binomial, and you're getting at it, but it's more general than that. Lots of interesting responses. But what I'm getting at is that we can actually add like another variable in here and still call it a polynomial. Like x plus like xy squared minus 5z cubed y plus x squared. This is actually a polynomial. And this is a polynomial in 3 variables. All right, a lot of people got at it with the binomial expansion. This is really just a 2-variable polynomial. See, because each term is just a product of the simple terms. Yeah, we call these multivariable polynomials. And you see that like we're never breaking from the structure. And the structure is like we have x raised to a power, right, y raised to a power, constant term if necessary. And then we're just repeating that for each single term. Then the end should be y cubed. Thank you for pointing that out. So we have all these different types of polynomials. In practice, what we're going to focus on is this, because this is the type of polynomial that algebra focuses on exclusively. And when I say algebra, I mean algebra class in school, the one that we all love. So yeah, and it turns out that these actually have some nice applications. All right, an example is, let's say you have a ball and you throw it, or let's say you have a cannon and you like use it to fire a ball like that. It turns out that this ball follows the trajectory of a parabola, assuming like no air resistance or like other like factors, of course, but we don't really worry about that. Right, so knowing how to like be comfortable with these expressions and manipulate them do have like actual applications. All right, but let's sort of explore what we can do with them. But first, we need to discuss the notion of a degree. Can anybody tell me what a degree is? How would we define the degree of the polynomial? The highest power of the variable. I'm seeing that's from basically everyone. Great. So we would say the degree of this expression is n. What is the degree of this expression? I'm seeing a lot of 3s, but I'm also seeing some 4s. And the 3s I see come from this, because this is just the highest exponent. But it turns out that the answer is actually 4 because that definition I told you was incorrect. All right, the definition is correct when we're looking at one variable polynomials like this. That works perfectly fine. But here, we have to take the sum of the exponents of each term. So the degree of this one would be 1, because there's only one exponent. The degree of this term would be 3, 1 plus 2. The degree of this one would be 4, 1 plus 2 plus 3 plus 4, or just 3 plus 1, sorry. And the degree of this expression would be 2. So the degree of this polynomial actually ends up being 4. And this is something that comes up when you work with like symmetric expressions and things. That's all we covered in a much later time, possibly. And have actually already been covered in the introductory and intermediate classes. Degree is a really important concept there. Where did the toolbar go? There we go. All right, so let's erase all this. And before we get to the math, we have a final like special term to talk about. And that term is, oh, you can see my screen backgrounds. That's interesting. The final term that we have to talk about is the Monic polynomial. And all that Monic basically means is that the coefficient in front of the term with the highest degree is 1. So this a of n value is equal to 1. So examples of Monic polynomials: x, x squared, x cubed plus 5. Not Monic polynomials: x plus 5x squared, x plus 2x cubed plus x to the second power. All right, you see that like these highest terms, their degree is 2, or the coefficient is not 1. And this is the case for a lot of polynomials, but fortunately, this is fine because we can actually turn them into Monic. And the way we do that is we factor. Like so. And now you see these coefficients are like slightly like not nicer, but sometimes when we're dealing with these expressions, it's actually like more or less fine. So now that we've looked at this, let's do some math. So let's say we're gonna start by looking at roots. So I guess we have more terminology. The roots of a polynomial are the values of x for which the expression equals 0. So we could write it like p of x equals 0. This is normal convention to define a polynomial, but let's give an example. X squared plus 7x plus 12. All right. And you can also call these like solutions to this equation or zeros. They're all really the same thing. The reason that they're called zeros is because when you graph it, the roots in these zeros line up exactly. So now, can anybody guess any particular values for that work here? A lot of people are giving me the answers because they know these techniques. That's excellent. Because there are techniques that we can use to get these quicker. And it turns out that if we plug in -3, this will work. Now, why is that the case? Well, let's go ahead and plug it in. -3 squared is going to be equal to 9. All right, 7 times -3 is -21. 12 is equal to 12. And when we add these up, yeah, it equals 0. So, cool, we found one root. Are there any others? -4, I see. All right, let's test that. Yep, it equals 0. Good job, everybody. Are there any others? Any other like things that we can plug in here? I see a lot of no's. So what you're telling me is that there are only 2 solutions here. The degree of this polynomial is 2. That's interesting. Let's keep that in mind. So let's go and like see how we can find these. So let's imagine that we're taking this product, x plus 3 times x plus 5. The way that we take products, of course, is going to be sort of FOIL type arguments, which is the distributive property a bunch of times. And we take these 4 products. So what we get, x squared plus 5x plus 3x plus 15, or x squared plus 8x plus 15. This is interesting. We've just established this equivalence. And it also shows that this polynomial can be thought of in a simpler way. right? Instead of thinking about this, we can think of it as a product of two simpler terms, and getting simpler is always better. Well, in most cases, but for our purposes, yes, simpler is better. So let's say we wanted to find the roots of x squared plus 8x plus 15. That's going to be the same thing as this question. Right? Because we said that these two expressions are equivalent. But look what happens when we look at this. All right, we have like one number here and another number there whose product is equal to 0. And being equal to 0, like having two numbers multiply to 0 is really cool, because this means that we know that one of these two numbers has to be 0. Think about it. If we have like this is like equal to 1 and this is equal to 5, then the product's 5. And that means that we can do casework. So what are our cases? Well, we know that one of the factors has to be 0. So let's say we're looking at the cases where x plus 3 is equal to 0. Can we solve this? And I'm going to hope that we can. Because what we do is, of course, subtract 3 from both sides. We get that x is equal to negative 3. Nice. And because when we plug it into here, we know it equals 0. This entire thing is equal to 0. So what's our other case? Case 2? X plus 5 is equal to 0. All right, and then similarly above, we get x equals negative 5. So what we've done is we just found these two solutions of our original quadratic. And we know that these are the only ones because they have to work here. So that's cool. So we see that looking at the factored form was actually a lot easier than looking at this form, where if we just saw it like this, all we'd be left with is just guess and check, guess and check, guess and check. Nobody likes that. So now here's the question. Can we factor every single quadratic? And the answer is actually yes, except it doesn't always look nice. So it turns out if you do the math, that x plus 1 plus root 5 times x plus 1 minus root 5 is going to be equal. Whoops. Oh, no, no, no. Don't crash, don't crash, don't crash.
So apparently Justin is having some technical problems. So I will pick up where he left off, or at least I will try to. Okay, so and or so, and I hope that Justin will get his computer up and running soon. In the meantime, let me hang on, everyone. Give me a second. Oh. Justin will be okay. Justin is back.
Hi, sorry about that. Hopefully the recording doesn't get too garbled. Yeah, I wonder how that's going to work out. But anyway, here we are again. So I should continue with what I was saying.
Yes.
All right. So now, what are we doing? Oh, wait. Yeah, that's right. We were talking about polynomials and factoring them. Okay, cool. So it turns out that we can actually factor them. But we're going to have to do some work in some cases. My PC is bad because I am bad. So what is this magical factored form? We're going to call it x plus a times x plus b. Or actually, be a bit more proper and say x minus a times x minus b. The roots are going to be x equals a and b. Hopefully, you can all solve one variable linear equations like this. But the question is, how do we get it to this form? Well, we can use the ever immortal trick of comparing coefficients. All right, so the simple way, and I'm actually going to write it as x plus a times x plus b because this, for all intents and purposes, is what we want. So ignore this for now. So this is equal to, x squared plus a b times x plus ab. So let's compare it to x squared plus 7x plus 12, those two numbers that we had from earlier. So we want two numbers that add up to 7 and two numbers that multiply to 12. And I think you all know what's coming, but still, what are those numbers? Four and 3. Excellent. Yeah, 3 plus 4 equals 7. 3 times 4 is equal to 12. Excellent. So basically, by comparing these coefficients, I know that I can write it like that. And then, of course, the roots are -3 and -4, just like we found earlier. So let's try it on a different example. What's a good polynomial? Yeah, let's factor x to x squared plus 40x plus 41. Or no, my bad. Better one. X squared plus x plus 41. Hmm. I'm seeing a couple people submit things. I see x plus 1 times x plus 40. Good starts, but we want the sum to be this 1 right here, not the product, not the constant term. 40 and -1, those don't sum things. I'm saying it's imaginary. Huh, that's weird. How are we going to factor this? And the answer is factoring fails to be nice here, as many of you guessed. So we're going to have to rely on a couple of other methods. All right, and I'm going to present two of them. All right, one of them will be completing the square. The other one will be the new quadratic formula, which is a thing, and I really want to present it all to you. But oh, this is interesting. You can sort of factor it like x times x plus 1 plus 41. But this is not entirely what we want, because when we set this equal to 0, we can't do that easy case work like before. Like we can't say like x is equal to 0 or x plus 1 is equal to 0, because this term just gets in our way. So let's take a look at completing the square. So completing the square looks at this following factorization. X squared plus 2ax plus a squared. And the idea behind it is that we want to get this to look as much like this as possible. And what this involves is getting this x squared term and this x term equal. So for this x squared and this x term to be equal to this x squared and x term, can you all tell me what a has to be equal to? What we want is different color, these coefficients to match up, which they already do. And we also want these coefficients to match up. So what value of a will allow us to achieve this? See 1/2? Yep, that's exactly what it is, because multiply, if you have this 2a expression and you multiply by 1/2, you get 1, which is right here. So we know that a in this case is going to be x plus, or just 1/2 squared. So that's x squared, good, plus x, good, plus 1/4. Not so good. We have a 41 here and a 1/4 here. But we really, really want to make it look like this. So we apply wishful thinking. If we want 1/4, why not just like subtract 41, move the 41 to the other side, and add 1/4. Like that. Wow, look what we have on this side. Can anybody tell me how we can simplify this? Yeah, we can actually factor this, and we already know what the factorization is because we wrote it up here. X plus 1/2. squared is equal to negative 163 over 4. So what do we do with this equation? What is our next step? All right, I think everybody so far has said take the square root of this operation, and everybody is technically wrong. Square roots don't work well with this. What you do is you think what two values when squared can equal this. So the morally correct way, like taking the square root is a way to think about it, I guess, but I want to be morally correct. So what you should think is x plus 1/2 is going to be equal to I root 163 over 2, or going to be equal to negative I root 163 over 2. And this is actually simplifiable. Like the way that all of you were taught to write it is in the following way. X plus 1/2 is equal to plus or minus I root 163 over 2. Why did I write 136? But saying you go like that and then you go like that, you really can't do that. It's not great notation, and that kind of thinking might lead you to mistakes. So if we solve these equations, we actually get our two solutions. And if anybody is confused on what I mean about what this whole I business is, I believe there is a lecture on complex numbers with a while back. I is defined. I is a number such that I squared is equal to 1. No, that's not what I meant. I is a number such that I squared is negative 1. It's like an entirely new construct. It's like some people like to write it as this, but that's kind of weird, and I guess it helps the understanding. It's like, think about defining a new number, and then it's possible to write solutions using that new number. So congratulations, we had just found our two solutions. That's cool. So this method of completing the square, looking at this factorization, figuring out the value of a that makes these first two terms match up, then using wishful thinking to add or subtract the remaining term to make this work perfectly, then taking the square root of both sides, sure, and solving for each individual solution. Wonderful. But I did mention there was another way to do it, and that is the way that I'm going to present to you now. Did I get the second solution wrong? Oh, I see. Sorry, I meant this. But everything leading up to that should be correct. All right, the second method that I'm going to present to you is the new quadratic formula. Now, this, about 8 to 10 months ago, became a thing when the professor Pochant Low published an article or two about it, and it kind of blew up, sort of blew up on social media as big as any math thing can. Pochant Low is noted because he is the coach of the United States International Math Olympiad team, and has been for the past several years.
And he also has developed an excellent contact tracing app called Novid, which we hope would, if everyone got the app, it would help stop the spread of coronavirus. So you should look that up.
99.6% success rate, according to its testing, which is incredible. Oh, did I screwed it up again? Oh, okay, whatever. I'll get it right this time because we're going to be using the same polynomial, but a different method. All right, and what we're going to do is we are going to look at this factorization again. All right, we can take a look at these roots and say that they're just p and q. So how does this look? Like that. So the nice thing about this is we can compare these coefficients and we can get information. So can anybody tell me what p plus q is equal to? Just look at this coefficient and look at this coefficient. And you should get -1, and that's absolutely correct. So the nice thing with this expression is that we can think of this as an average. So we know the average of these two numbers is 1/2. Or -1/2, as I should have said. So let's say p is equal to -1/2 plus some number. And then what is q going to be equal to? If p is equal to this, and we know that p plus q is -1, what is q equal to? Nobody is responding. I guess I've really stumped everybody. If this is like what we assigned to be p, this is like -1/2 plus z. Oh yeah, this is a variable, by the way. Yeah, okay, there we go. I was just making I just wrote it badly. We know that q can be expressed as -1/2 minus z. And hopefully you can see why I chose these expressions. When we add these, we get -1, yeah, but there's this nice symmetry going on, this whole plus minus thing. So now what we're going to do, this is the real kicker. We're going to multiply these two together right here and set it equal to 41. And this gives me a good chance to talk about a special type of factorization called difference of squares. That's exactly what we have here. Difference of squares basically says the following. That this expression can always be factored. But if you don't know that, don't worry, because all we have to do here is just FOIL the heck out of this thing. And eventually we get 1/4 minus z squared is equal to 41. But this equation is actually really, really easy to solve because there's only one variable term. We get z squared is equal to -163 over 4. Okay, somebody asked me a question, and can't you write x or y instead of z? This is a good question just based on like how I use my variables. X, you definitely don't want to write x here because x is already defined in this part, and you want to keep your variables distinct. Y, I would like sort of like shy away from because sometimes we say like y is equal to that, and I want to kind of be distinct from that. So z seems like the most natural option. But in any case, I think the most important reason was that the original proof that I read of this used z, so I copied that. But yeah, my z's do look like 2's, unfortunately. But we can solve this. All right, and this time it's like okay to take the square root of both sides. Yeah, okay, that's a great suggestion. I get it every time. Go like that. All right, and it turns out the plus or minus doesn't matter because that's taken care of in this section. Just haven't gotten into the habit of doing that. So we know, once again, let me erase this, that p is going to be equal to -1/2 plus I root 163 over 2 And Q is going to be equal to negative 1/2 minus I root 163 over 2. All right, and hopefully I got the two solutions right this time. So what was it that we did here? This method was a bit more involved than the previous one, but it turns out to just be slightly faster. We can't use the quadratic formula because the quadratic formula is worse. All right, what we did here, this like goes into like so much more structure. All right, we have this like whole nice thing where like we have the sum of the roots is this and the product of the roots is that. All right, we are able to reduce everything to a really simple difference of squares like we do here. And then once we have that, the top line instead of the box. Yeah. Yeah, because this method actually turns out to be super clean. And you get the same result either way. So if you like the quadratic formula, use it. But completing the square and whatever this is, the new quadratic formula, I suppose, there's a certain symmetry to this argument that's kind of nice. Like invoking these symmetric structures, making it so that you have a really easy quadratic to solve instead of a horrendously complicated one. So that's all you need to know to get started on solving any quadratic ever. But we said that there were a lot more than quadratics in the polynomials. What if we have cubics? So what's a good cubic? Let's say x cubed plus x squared, 2x squared plus x plus 2. How would we solve something like this? See somebody say it's use the cubic formula? I don't think so. So a lot of people are saying grouping, and yeah, in this case, it's not too horrible to find the two. If you like try and factor these, you see that they magically have a factor. So we can factor again, and we get x plus 2 times x squared plus 1 is equal to 0. Yeah, but in general, these don't factor nicely. So if you don't believe me, try factoring this for a few minutes and see how far you get. So I see solving this. Oh, look, we have a quadratic that we can solve. I see people say that x equals -2 and I are the solutions. Is this an accurate statement? It's not the most accurate, actually. You're missing one. People who said that. Because it turns out that we also have -I. And we have to include that because this is a fundamentally different number. But we see that, yeah, this has 3 solutions and the degree is 3. That's interesting. So it turns out that this is a general rule. And this is very, very hard to prove. But fortunately, people have done it for us, so we don't need to do it. So we have this polynomial, n degree polynomial. And the degree of polynomial has n factors. And I'll call them linear factors. This is not de Moivre's theorem. Can anybody tell me what this is called? This has probably like the most epic sounding name in every theorem ever. It's not the rational number theorem. This is the fundamental theorem of algebra. That just sounds cool. Right here. All right, and the reason I say factors instead of roots here is because like usually they're the same thing, but what if you have the equation x squared, x minus 1 squared equals 0? This has one solution, but how can that, but it has two factors. So we say that one has multiplicity 2 in this case. Because we can think of the x minus 1 factor as being counted twice. Double roots, exactly. So this means that we can always factor this quadratic no matter like how we do it, as x minus like the first roots times x minus the second root times x minus the third root. By the way, did anybody manage to figure this out? I thought not. So yeah. Are there any more topics that I can cover? Like any more basic topics? Because there are a couple that I can think of, but they're long and require a lot of setup. So are there any like polynomial related things that you guys would like to think about? How do we factor this? I have no idea. I'm pretty sure it's like they're like really, really horrible numbers. But yeah, does anybody have any requests before I go into like this last content stuff? No requests? Okay, so let's go to long division. Another thing with polynomials. So give me a couple seconds. And we'll get started. So polynomial long division is really useful when we're looking at factors. So let's consider the equation x to the fifth. Let me figure this out really quickly. I don't want to spoil the answer. Sorry. Fifth plus x to the fourth plus 2x. No. Okay. X to the fifth plus x to the fourth plus x cubed plus 2x squared plus 1. All right, and let's try and factor this. Well, don't try, because it turns out if you go and like plug in a bunch of numbers, it's not gonna work out. But let's say I told you magically that one of the factors was x squared plus 1. And you wanted to figure out what the other factor was. How would you do that? The answer lies in polynomial long division. Now, I'm sure all of you remember the division algorithm from grade school, but we're going to do something really similar here. So we're going to take a look at this leading coefficient, this grand impressive x to the fifth. What can we multiply this x squared by to get something that's close? We can multiply it by x cubed. All right, what is x cubed times x to the fifth plus 1? X to the fifth plus x cubed. And you see that I'm taking extra care to get the terms aligned. When we subtract, we get x to the fourth plus 2x squared. So now, what do we have? What can we fit in here? We can fit in an x squared term, maybe. Then at the end, we have x squared plus 1. And technically, I should have written it like this. That's also an important thing to note. So we can't multiply by an x term here. We can multiply by this 1. And when we subtract it, we don't end up with a remainder at all. So this tells us that this is equal to x squared plus 1 times x cubed plus x squared plus 1. Polynomial long division is, yeah, basically this. So are there any other questions about anything else that we covered here? I know this was like pretty basic, but this is the fundamental series, of course, and I wanted to just cover all. Make sure we got our bases covered. No other questions? All right, if that's the case, then I think I'm going to end here. Thank you all for coming. Hope you got something out of it. Whether it was learning or like being able to boss me around when I do something incorrect. And we will see you all next week for, oh yeah. In case some of you are not in the Discord, next week is going to be a individual problem review. And the problems that we're going to be reviewing are those that are found at the end of each handout. So you have the opportunity to choose problems that you want us to review. And I sent a message about it in the Discord, so read that, follow the instructions. Nobody has done it so far, but we'd like to see you guys choose the problems that we cover. So yeah, other than that, I think that's all we need.